In the previous video, I introduced you to the Fisher-Pittman type randomization test for K samples. Now we're going to look at the Kruskal-Wallis test, which is also for K independent samples. One of the most commonly used designs in behavioral and social research involves the comparison of scores in K conditions where K is greater than 2. The Kruskal-Wallis test is based on ranking observations. As such, it can provide more power than the parametric one-factor ANOVA when population distributions have higher kurtosis than the normal distribution. And just as importantly, if not more so, it can contain the type 1 error rate when we do not have a normal distribution. The required package to follow along is the R package coin. Here's the setup. You should be familiar with this from the last video. We draw random samples from K populations where K is greater than or equal to 2. That is, we could have K independent existing populations and we draw a sample from each for comparison purposes, or we might draw one sample from one existing population and then create from that multiple samples through randomization, with each sample representing a potential population, with the exception of the control group, which would represent not the potential but the existing population. We make independent observations within each sample, and we have a quantitative response measure. Here's an example. A study of the effectiveness of metaphors compared 3 conditions: a control condition, an advanced metaphor condition, and an extended metaphor condition. Participants in the control condition received a difficult textual passage. For the advanced metaphor condition, the same passage was preceded by a familiar metaphor. In the extended metaphor condition, the metaphors were embedded in the passage. All participants completed a comprehension test about the passage. The hypothesis here is that the median of the first population is equal to the median of the second population is equal to the median of the third population. This could be extended if we have more populations, so that we could also look at the equality of these 3 groups to a fourth population median, and so on. The alternative hypothesis is that the medians are different for some of the populations. For a hypothesis about a shift in medians, the distributions must have the same shape. If they indeed do have the same shape, and not only that, if the distributions are symmetrical, this test about medians could be a test about means, just like with one-way analysis of variance. The null hypothesis here could be that mu1 equals mu2 equals mu3, with the alternative being that some of these are different from one another. Without shape identity, or with an ordinal response measure, because now we're going to be using ranks, the null hypothesis is that the probability of obtaining a score from one condition being greater than scores from the other condition is equal for all conditions, and the alternative is that it is not, that we are more likely to get higher scores from one of the conditions. Now let me introduce you to the Kruskal-Wallis H statistic. There are popular formulas for the H statistic when there are no ties, and there are also popular adjustment formulas for when there are ties. I'm going to show you a different way to calculate H that doesn't rely on any of these formulas and is a single formula based on sums of squares that handles a situation with or without ties, so you don't have to have alternative formulas. First, we rank all the observations. We put them all together from all the different conditions and then rank them. And then we use this formula based on ranked observations. We look at the sum of squares between and divide that by the sum of squares total divided by n-1, which is the total degrees of freedom. Let's look at an example. Here's our control condition with scores of 9, 10, 6, and 11, our advanced condition with scores of 13, 5, 7, and 8, and our extended condition with scores of 15, 12, 17, and 14. Here on line 5, I am creating a condition factor for each of the 3 conditions. Here on line 6, I am combining the scores so that on line 7, I can rank those combinations of scores. On line 8, I'm then running a linear model and getting the analysis of variance table out of that model. That is for the purpose of being able to extract the individual sums of squares. If I was writing a function to do this, we can actually save this ANOVA table and extract the sums of squares that way so we don't have to do it by hand. But here I'm just doing it by hand. The sum of squares for the between groups is 85.5. The sum of squares total is the combination of the between and within sums of squares. That is the between sums of squares and residual sums of squares. That's the total. Similarly, the total degrees of freedom is the sum of the degrees of freedom for between groups and within groups, and that's 11. So our H statistic here equals 6.58 using the formula I presented in the last slide. What we do is calculate H for each possible combination. If you watched the last video, you know we have almost 35,000 combinations, so that can be quite a task. What's different here is that the combinations, which are based upon sample sizes, would actually remain the same, assuming no ties, for all experiments or all studies that are done with those same sample sizes, because we're using ranks. So for 12 scores, you have the ranks 1 to 12, no matter what those 12 scores are and no matter what the study is, as long as you're using 12 scores. That makes it easier than looking at original scores because we only would have to calculate such things as critical values one time, and that would work for any study that uses the same sample sizes. We sort the values of H for all of our combinations, calculate the cumulative probability, and construct a rejection region such that the probability that H is greater than or equal to the critical value is less than or equal to alpha. This ensures, as do all the randomization tests, that we maintain our type 1 error rate at something less than or equal to alpha, our nominal type 1 error rate that we chose as our tolerance for errors. As with the Fisher-Pittman test, the number of permutations gets large very quickly, but as I've explained, the critical value could be calculated one time for any combination of sample sizes, and that's all you would need to have it for every other study that has that combination of sample sizes. That means it's feasible to create exact critical value tables, and indeed, Meyer and Seaman have done that for 3 and 4 groups, or we can just use the Monte Carlo approximation. Here's an R function. Base R provides a function for doing the Kruskal-Wallis test, but note that it is an asymptotic approximation. That is the only approximation it will do. And for our particular data, we're getting a p statistic of 0.03. We could use the coin library for a Monte Carlo approximation. Here I am not only using the approximation, but I'm also specifying a larger number of resamplings, namely 100,000, and we're obtaining a p-value of 0.026. Note that the chi-square value that we see here for both of these are identical. That value that's listed as a chi-square is actually the H statistic. 6.5769. If you go back here to where I calculated, you see 6.58. It is the same as the chi-square that we are seeing here. A little bit more about R functions for these randomization tests. In the previous video about the Fisher-Pittman type test for K-samples, I used the one-way test function. Let's try it again, but first ranking our observations and asking for an asymptotic approximation. If you look at the asymptotic approximation that we obtain, 0.03731, you'll see it's the same thing we got back here for the p-statistic using the base R Kruskal test. And if you see the 6.5769, you'll see it's the same thing we got here. What's going on? This is the one-way test. This is not Kruskal-Wallis. Well, we are doing Kruskal-Wallis because we ranked our observations first, and what's being calculated, what this tells me, is that this is an H statistic being calculated. And that would be true even if you're using original scores. It's not an F statistic if you're using original scores. It's an H statistic. All of the K-sample asymptotic approximations use the H statistic, and then they compare that to a chi-square with K-1 degrees of freedom. That is, they compare it to the mathematical model, the chi-square with K-1 degrees of freedom. Now, I do need to point out that when I say the H statistic, I'm not talking about the H statistic using the formula that Kruskal and Wallis used, because that was based upon having ranks. Rather, I'm talking in a more general sense about the H statistic using the formula that I presented, where H is calculated using sums of squares between divided by sums of squares total divided by degrees of freedom total. When I say we are using an H statistic for all of these methods, that's the formula that I'm referring to. If we're not using ranks, we're not actually using the H statistic as defined by Kruskal and Wallis. Nonetheless, I'm pointing out that what we're calculating here with original scores or any other scores is based upon the formula I provided and not the formula for the F statistic. You may have also noticed that the asymptotic approximations are quite a bit different than the Monte Carlo approximation. Here we had a 0.037, here we had a 0.026. That may not seem like much of a difference, but if you think about working with small numbers like this, it's a substantial difference. So what should we believe? Should we go with the asymptotic approximation or the Monte Carlo approximation? Meyer and Seaman, the same people who constructed the exact tables, also demonstrated in a 2013 publication that the chi-square with K-1 degrees of freedom approximation is not the best we can do. So I recommend using Monte Carlo results. There's another function in the coin library for conducting a K-sample normal scores test. Let's use it. I'm going to go straight to the Monte Carlo approximation for the reasons that I stated above. The function is normal underscore test. Here I'm using a Monte Carlo approximation with a resampling 100,000 times, and I'm obtaining a p-statistic of 0.02427. I do not need to give this normal scores. It does it automatically for us. As you know from previous videos, we may want to use this test if we believe that our population distributions have lower kurtosis than the normal distribution. Some items of note. The test statistics for the methods in this family of tests is more heavily influenced by differences in location than by differences in distribution shape. What do I mean by the family of tests? We've looked now at 3 K-sample randomization tests: the Fisher-Pittman, the Kruskal-Wallis with ranks, and the normal scores test with normal scores. We also know that in order to test a hypothesis that the medians are equal in the conditions, we must have the same distribution shape. But what I'm showing you here is that research has demonstrated that if you have differences in shape, there is going to be some influence on the test statistic, but that influence is not nearly as heavy as is the influence in differences in location. That's reassuring and tells me that I could use a null hypothesis about medians in each of the populations and whether they're equal, and have a little bit of differences in each of the shapes of the distributions, and I'm still going to have a fairly accurate test. Another item of note: if we set Z sub W as the large sample Wilcoxon statistic, that is the asymptotic value of the large sample Wilcoxon statistic for 2 samples, and square that, we get H. That should sound familiar to you. If you take a T and square it, you get an F statistic. So the same type of equivalency that applies in the parametric world appears here in the nonparametric world when we're using ranks. The large sample distribution of the F statistic, when we conduct the Fisher-Pittman type test for K samples, is F with K minus 1 degrees of freedom and N minus K degrees of freedom. That is, the large sample distribution of our F statistic from the Fisher-Pittman test is the same as what we use when we do one-way ANOVA. The large sample distribution of the H statistic is a chi-square with K minus 1 degrees of freedom, but as I've already mentioned, you're going to be better off using Monte Carlo approximations. Keep in mind when you're making choices about these tests that all the asymptotic relative efficiencies are consistent here as they were in the 2-sample randomization test and the 1-sample match pair test. That is, if we have light tails, light kurtosis, we want to go to normal scores. If we have heavier tails, heavy kurtosis, we want to go to ranks as possibly giving us more power than the parametric test will. And the parametric test will be most powerful when we have a normal distribution. However, the power of the normal scores test and the original scores test will equal that of the parametric test when we have a normal distribution.